Hey guys, welcome to the second video in the thermodynamics series. Now, in the last video, we laid out some very important ideas that are crucial to move along in thermodynamics. So if you haven't yet watched video 1, please go back and do that. We laid out three basic areas: the transfer of energy, which can be seen as the movement of heat or work being done. We called these processes that change the state of the system. We then also looked at the idea of the conservation of energy. And we said that for a particular system, the internal energy will change by the amount of work that's done on the system and the amount of heat that is moved into or out of the system. This was known as the first law of thermodynamics. And lastly, we took a look at a system as a bunch of little particles from the perspective of the groundwork of the kinetic theory. We basically said that many different microstates could contribute to the same macrostate description. Now, whereas the last video was very broad in its approach to thermodynamics, this video we're going to narrow down on this idea of temperature versus heat. Let's get into it. So at the end of the last video, I challenged you to go to fet.colorado.edu and to try to come up with your own definition of temperature. Now in this video, as the title implies, I'm trying to compare and contrast heat versus temperature, because these terms are often used interchangeably and oftentimes incorrectly. And to be successful in thermodynamics, we have to have a very distinct definition of each. Now, one thing I already knew about heat from the previous video was that heat was a form of energy exchange or energy movement between a system and another system. And so I realized that in order to take any measurements in this experiment, I would need to figure out how to adjust either the heat or to adjust the temperature. Now, this is not a chemistry video and it's not a physical chemistry course, so I'm not going to get into too much detail about how we release heat, but what I do know is that in the simulation, I have the opportunity to heat the system or to move energy into the system, or I have the opportunity to cool the system, which actually turns out to remove energy from the system rather than to provide coolness as some substance to the system. Now, how I came to that conclusion is that, one, I introduced particles into the system, and then by applying heat to the system, what I realized was that the particles began to move faster. That was my indication that energy was being added to the system, because I already do have a mechanical understanding that kinetic energy has to do with movement. Now, the more important one is that when I cooled the system or put ice adjacent to the system, I noticed that the particles started to move a lot slower. And that's how I knew that energy was removed from the system. Now, we are going to get into a lot more detail later about physically adding particles and removing particles from the system and how that will affect different measurements of heat and temperature within the system. But for now, what I'm going to say is that I have a fixed system of, let's say, about 90 particles. And within this system, when heat is added to the system, the particles begin to move faster. So I'm not physically adding a substance in the form of heat to the system. More so, I'm transferring some kind of energy. And it's not a physical addition of something that has mass to the system. And when I cooled the system, I wasn't adding some cool ether to the system, if you will, from a more Victorian understanding of science, but I was rather removing heat from the system. So cooling something down does not mean applying coldness to the system in any sort of way, but rather removing heat from the system. Now we're going to talk about how that would occur in a little bit. So my first observation was I add heat to the system, the energy of the system has increased in the form here of kinetic energy. Now to temperature. After adding heat to the system, or adding energy to the system, I noticed that the temperature did change. So by adding heat to the system, I noticed that the particles are moving faster, and when the particles are moving faster, I noticed the temperature increase. So I decided to see if there was a mathematical relationship between the speed of the particles and the temperature. Now, what was important to note, and this is going back to the kinetic theory, is that the particles are moving randomly, or at least they appear to be. They're also not interacting with one another in the form of forming bonds or anything like that, but they do appear to be having elastic collisions. Now, that means that they're not losing kinetic energy when they collide with the walls of the container or with one another. So other things that we're going to add to the kinetic molecular theory are that particles within the gas do not react with one another and that they have perfectly elastic collisions. All of these different things that I'm doing is simplifying the fluid here so that I can build a model from the ground up, adding complexity as I go. Another thing that I noticed was that I was really measuring the average speed of the particles, because it appears as you watch them move around that they're definitely not all moving at exactly the same speed. And so this idea, keeping in mind that there's an average speed here, is very important. So my first mathematical graph was to measure the relationship between the velocity of the particles and the temperature of the gas. Now, I was using temperature as an independent variable. So I knew that it couldn't be adjusted on its own. In other words, I have to add heat, I noticed, to make the temperature go up. And when that happened, I noticed the particles moving faster. So it's the whole chicken or the egg thing. Is it the speed that makes the temperature go up, or is it the temperature that makes the speed go up? Well, what I'm starting to realize is that the speed is making the temperature increase. Now, in other words, the temperature is really a measure of the speed in some way, it appears to be. But we're getting ahead of ourselves, so let me show you this graph. And what I found was that the velocity versus the temperature had a square root relationship. In other words, velocity is equal to some constant times the square root of temperature. That appeared to be pretty standard for a variety of different speed and temperature measurements that I took. So far, I can see that there is some sort of relationship between the average speed of the particles and the temperature of the gas. But I know that if energy is being added to the system in the form of heat, and I'm observing that the kinetic energy is changing, I know that the speed can't be the only thing that is influencing this temperature. Mass is part of kinetic energy as well. So I'm going to change the kind of gas to a lighter species of gas. In other words, instead of having larger molecules, gas molecules, I'm going to have lighter gas molecules. I'm going to put the same number of molecules in the chamber and see if I observe the same effects. So at this time, I challenge you to pause the video and to try to predict, will the speed of the light species at the same temperature as the heavy species be the same? So in other words, let's say at 300 Kelvin, will the speed of the light species be the same average speed per particle that I measure for the heavy species or not? And why do you think that is? So after doing this, I did get the same graphical relationship, but I will tell you that the particles were moving a heck of a lot faster. So when adding energy, although I saw the same relationship in the same shape of increase, I definitely saw individual values much higher, sometimes at least double the speed. So another way to look at this, what I found was that a heavy species of gas at a temperature of 300 Kelvin had particles that were moving a lot slower than a light species of gas at 300 Kelvin. They were moving a lot faster. So what this leads me to believe is that temperature is not really a measure of the average speed of the particles, but more so a measure of the average kinetic energy of the particles. This is very apparent because I can measure the same temperature but two different speeds if I have gases that have two different masses. And that's pretty interesting, and I think fairly significant as I look at this. So at this point, what I can say for sure is that temperature is a measure of the average kinetic energy of a particle of gas. Now, it's very specific here because I'm starting to notice that it's not the average kinetic energy of all the particles, but rather the average kinetic energy of a particle within the gas. And if I look at heat, it's more so a measure of energy as a whole. So if I were to add, say, 100 joules of energy to this system, I realize that I'm not giving that 100 joules of energy to any one particle, but to the system as a whole. So that is quite distinct. So far what I've found is that temperature is really a measure of the average kinetic energy of a particle, and heat appears to be the amount of energy that I can add to the system as a whole, which will result in a difference in temperature. So finally, I'm going to try to link mathematically the average kinetic energy per particle to the temperature of the system. So taking my graph for average kinetic energy of either the light or the heavy species and looking at it in relation to the temperature, what I find is that there is a very unique constant on this graph. Now, I'm not going to get into a lot of the detail about how I derived this here, but if you would like to watch more about this, I have one of my other videos linked below that goes into a rigorous mathematical development of this idea. What I find the mathematical constant between average kinetic energy of the particles and temperature to be is actually 3/2 times what we know as the Boltzmann constant. So 3/2 times K sub B. So the equation becomes the average kinetic energy of a particle is equal to 3/2 K sub B times temperature. Now we'll get into a little bit more detail about what that 3/2 means and what the Boltzmann constant is. But for now, we're going to just accept that there is some sort of constant of proportionality, that no matter what species of gas I use, I still find the same constants that relate the average kinetic energy to the temperature of a particular gas. So my summary so far is that as I add heat to the gas, I'm adding energy to the gas as a whole. And then the temperature is really measuring the average kinetic energy of a particle within the gas. So in order to know how much heat was added to the gas, if everything else is staying the same, what I actually find is that I can take a measurement of the internal energy of the gas, because the internal energy of the gas, according to what we talked about in the first video, the internal energy of the gas should increase or decrease by the same amount of heat that I added to the system. Now, this is of course assuming that there is no energy lost in the system and that there's also no other work being done. So any heat added to the system should change the overall energy of the system. Now, you might think that, okay, if I know the average speed of just one particle, if I multiplied that by however many particles I have in the gas, I should know the total energy or internal energy of the gas. And that is in fact correct. So if I take this equation, average kinetic energy is equal to 3/2 K sub BT, then multiplying it by N would say this now is the internal energy of the gas. So instead of just focusing on the average kinetic energy per particle, I focus on the total energy for the entire gas, which should equal the amount of heat added to the gas. So your challenge as I leave you for this video is to try to figure out when will heat spontaneously move. Now, if you can access some sort of calorimetry simulation, and hopefully you've looked at a calorimeter in chemistry. If you haven't, that's okay. But basically what it's going to be is a styrofoam cup that's pretty well insulated. And I'm going to heat up a piece of metal and measure its temperature, and then put that metal into a beaker or a styrofoam cup of water, and try to see if I can figure out how the movement of the heat will be. So in the next video, we will take a look at what the result is of the movement of heat or heat transfer and how we can quantify that.